right, good morning, everybody. It is time to start the Thursday plenary. Today's plenary is Rubin Research Spotlights. As a reminder, we have a code of conduct. If you experience or witness any violations of this code of conduct, please reach out to our code of conduct contacts. As a reminder for everyone in Zoom, just please remain muted unless you're invited to speak to ask a question. And use also, of course, the Slack channel that is for this session to ask questions of our speakers. You can post questions while they're talking, and then we'll see them once they're done. Another reminder of where the coffee breaks are, and a reminder that today is the last day for posters. It's the second day of the Wednesday, Thursday poster session, and the afternoon coffee break is the designated poster session where the poster presenters will be standing at their board ready to talk to you. There's a website there's a page in our website that's just about getting food for lunch. So as a reminder, the Slack Cafe is over in Building 53. Doing DoorDash is an option to have delivery to Building 53. Today's special bring your own lunch session with the EPO team is all about citizen science. So do join them during your lunch hour if you want to learn more about citizen science and the EPO team. A reminder of the convenient lunch options, ordering ahead at the Slack Cafe or ordering ahead for a complimentary sandwich delivery, with the reminder that orders have to be in by 11 a.m. You can't put them in until 10, and they have to be in by 11. And your first name in the order has to be Slack RCW Delivery, and Heather will go and get all of the sandwiches and bring them over, and they will all be at the registration table by 12 p.m. by lunchtime. So that is there as an option for you. Another reminder that Thursday after the plenary, 10:30 a.m. over in Redwood, that's the users committee meeting. Everyone is welcome to come to the users committee meeting. And in fact, the first 45 minutes or so is just a listening session where the users committee wants to hear from the users about your experiences with the Rubin Science platform and the data products and all the tools that we have for analysis. So this is your chance to say, what's good, what's working, what have you struggled with, what do you need to do your science, that kind of thing. The UC really wants to hear from you. And then if you are inspired to join the users committee, the call for nominations/volunteers is out with a deadline of Friday, August 7th. So it's next Friday. We want to get those nominations in, and all the details you can find in the forum about how to nominate yourself or someone else to serve on the users committee. Another reminder is that new this year, we're making use of the Friday afternoon with some Friday afternoon sessions. The idea is to see how it goes and then maybe implement this long term as a hack session, always on the Friday afternoon or something special. And this year, we've got a research software engineering mini course, a session on Rubin 2036. So looking forward to after the 10 years of the LSST. And then the other session is mentor training. So a full afternoon session on building your skills as a research mentor. So if you're here Friday afternoon, do consider checking out these special sessions. And with that, I'm going to hand it over to Louise to chair our plenary.
My name is Louise Edwards. I am a member of the Scientific Organizing Committee this year. It's been my pleasure to be part of the committee who has invited these 4 speakers. We have a variety of science topics, and I hope you enjoy. Our first speaker is Sean McBride.
Sorry. Okay, fantastic. Thank you so much. The mic is working? Okay, great. All right, thank you very much. And thanks to the Scientific Organizing Committee for inviting me to speak. Let's say a few words here. So my name is Sean McBride. I'm a PhD student at the University of Zurich. I also work as an LST camera support scientist and help to coordinate the Rubin TOO program. I want to talk today about how we can use LSST data to measure cosmology, but use it using a fairly unconventional way, using a combination of LSST data with gravitational wave data. So I'll start with the current cosmological model that we use today. We all know and love Lambda CDM. Lambda CDM is remarkably successful at explaining many features of the universe, dark matter, features, signals that we may see from inflation, along with dark energy. But there have been two recent results and two recent avenues that seem to show that our model of Lambda CDM is incomplete. And I will highlight at least the recent on evolving dark energy, but also a persistent 5 sigma discrepancy in measurements of the local acceleration rate of the universe, known as the Hubble constant. Now, there are two primary methods in terms of measuring the Hubble constant. One uses very local probes, the local cosmic distance ladder, and the other uses very distant probes, primarily through the cosmic microwave background. And despite both of these probes, we've measured H naught using these two different methods to over 5 sigma precision. So something here is clearly not right. Maybe it's a systematic, maybe it's a hint of evolving dark energy, or maybe it's something else entirely. Now, I'd like to propose, and we've already made some measurements, that gravitational waves can be a remedy to this tension. The main reason that the gravitational waves are useful is that they provide a calibration-free distance measurement to an inspiraling source, or a merger of two compact objects. So by looking specifically at the frequency of a gravitational wave, the frequency evolution of a gravitational wave, and the characteristic strain, which is the amplitude here on this figure, you can actually get a measurement directly of luminosity distance. And this is very important from a cosmology standpoint, since luminosity distances help us understand our cosmology better. Particularly for gravitational waves, much of the focus has been on addressing and measuring the Hubble constant, and so that's what we'll focus on for the rest of this. So there are two flavors of this, what we call standard siren measurement. We call it standard sirens, since similar to standard candles, we use frequency space or frequency space measurements. So in standard siren measurements, we typically augment our data using electromagnetic data from galaxy surveys like LSST, using either a bright siren method or a dark siren method. And this directly has to do, bright or dark, with whether we detect or do not detect a counterpart to a gravitational wave event. So I'll start with the bright siren case, which is this top row here. Typically with bright sirens, if you're able to detect confidently the counterpart to a gravitational wave, you can get a very highly constraining measurement of H naught. This has been accomplished once before. I'm showing here images from the dark energy camera campaign to try to image the counterpart to gravitational wave from 2017. So nearly 10 years ago today, a binary neutron star merger was reported by the gravitational wave collaboration LIGO Virgo Cagra. And within 24 hours, a wide variety of telescopes were able to image this counterpart here in NGC 4993. And this provided a direct measurement of the Hubble constant that's consistent with both of these measurements from the cosmic microwave background and the local distance ladder, but does not yet discern between one measurement or the other. And so this was the first demonstration of the standard siren method on sky using real data. Now it's been almost 10 years, and two very long observing runs have concluded from the gravitational wave observatories. And unfortunately to date, despite a large effort by many people, some of which are in the room here today, there's been no confident association or detection of an electromagnetic counterpart to a gravitational wave event. I'm showing here DCAM, which before the onset of LSST and the LSST camera was the primary discovery instrument and the ideal discovery instrument due to its wide field of view, very deep imaging capability, and the ability to scan the sky very quickly. Now, there's been a lot of questions or hypotheses about why exactly we're not discovering any additional bright sirens. It could be because the objects are too faint. We may be misunderstanding the emission mechanism. There's also the Poisson statistics that we have to live with, and that we likely got very, very lucky to identify a very favorable gravitational wave event in 2017. Now, hopefully, Ruben will try to address some of these issues. And so this is a little bit part of my work in the Target of Opportunity program, and where gravitational wave follow-up is a large part of this program. And now it's not just cosmology. There's many other questions that we would like to answer by detecting and measuring counterparts of gravitational waves. There's our process decay that we would expect associated with kilonova, many other things. And so LSST camera provides both the wide, fast, and deep scanning capabilities that allow us to detect and measure, characterize faint counterparts to gravitational waves. And so I'm showing here the scanning capability of a recent follow-up that was from November of this year. If you're interested in this one, you could talk to me or Shreya Anand, who's leading the analysis for this. What you're seeing here are observations that we were able to obtain over 800 square degrees in a little under 90 minutes using LSST. So we were able to scan 800 square degrees, approximately 10 degrees per minute. We did this in 2 bands, and we're able to get down to magnitude 24, which is to date the largest and deepest search for a counterpart to a gravitational wave. Now, if you want to get an idea of how deep we can go and what parameter space we're able to explore now, I'd point you to this figure, which is from a recent paper by Nick Vieira. And you can see the LSST observations are significantly lower here and allow us to probe fainter and fainter timescales. This allows us to be able to discover, characterize, and detect counterparts much later than we would be before. I showed DCAM before. Typical single visit image depth of DCAM is about 22.5 to 23. So while with DCAM, we can only detect things in the first day or two, with LSST-CAM and this proposed counterpart that we searched for, we were able to detect things, hypothetically, out until 5 or 6 days. Now, of course, we did not detect a counterpart associated with this event, but this does begin to demonstrate the discovery potential of LSST for electromagnetic counterpart follow-up. So I've talked a little bit about bright siren discovery. I want to talk and shift now to this idea of when we do not discover a counterpart, which is to date every single other gravitational wave event that we've detected. Now, this measurement, while not high fidelity and not as high signal to noise compared to the bright siren measurement, we can apply to every other gravitational wave merger to date. And while an individual measurement may not be very well constraining, by combining the results of 300 to 1,000 to many, many different gravitational waves, you can actually get a fairly good measurement of the Hubble constant. And so this is what we've been doing. So we began to apply this method first with the dark energy survey, which is a highly uniform, covers 1/8 of the sky. We were able to get an 11 to 12% constraint on the Hubble constant when combined with the one bright siren from about 10 years ago. Now, this was a very promising result, and I'd like to draw your attention to the fact that while the dark siren results, which is here in blue, may not be very well constraining, it has officially now surpassed the constraining power of the one bright siren that we have to date, which is shown here in yellow. And so now dark sirens have become more constraining than bright sirens on their own, and in combination, they provide a very good constraint on the Hubble constant. One thing that we're now piloting is trying to expand the area coverage. So we're starting to use the Delve Galaxy Survey, and this is under active analysis, so some of these numbers may change, but at least to date, this is the best precision that we've been able to get with the dark siren measurement. The hope is that with a few more gravitational wave events, we'll be able to bring this level of precision, which currently is at 11%, down to below 10%, so that we can at least be crossing that frontier. And all of the constraining power comes mainly from the gravitational wave information and the clustering information along your line of sight. And so where does LSST really help to leverage this ability? So our current limiting systematic on the galaxy catalog side of things is the level of photometric redshift precision, because this gives us an understanding of how well we can recover the local fluctuations that will correlate well with our luminosity distance distributions. And so I'm showing here at least the photometric redshift distribution with Delve. I have not yet gotten an opportunity to produce this kind of plot with DP2, but the hope is that by adding U-band, an additional band that can improve our photometric redshift precision with LSST, we'll be able to better recover local scale fidelity inside each of these individual gravitational wave lines of sight and get a better constraint for the Hubble constant through these analyses. So we've started these analyses with DP2. The wide area coverage that we're expecting with data release 1 is comparable to Delve, yet will be a significant upgrade in terms of the photometric redshift precision. This will be the gold standard galaxy catalog for the next 10 years for these kinds of analyses. So we're very excited about these analyses, and we're really on the precipice of something special. Thank you very much for your time today, and I hope I've been able to convince you that gravitational waves are an accurate measurement tool for constraining cosmology in the universe in support and in complement to observatories like Rubin. Thank you very much, and I'm more than happy to take the questions.
Thanks so much. And I'll just make a quick announcement that we'll save the questions till the end, just for the interest of time. And our next speaker is Burson Lupakdel.
Do I need to do anything? Play. Okay. Hi, everyone. This is Burçin Mutlu Pakdil, and today I will be talking about finding faintest dwarf galaxies with Rubin across all environments with the help of AI. So, but before first is first, why should you care about dwarf galaxies, right? So, because they are the most numerous galaxies, they are small, faint, they are the oldest and most metal-poor systems, and they are the most dark matter-dominated stellar systems in the universe. So they are amazing probes for galaxy formation threshold, galaxy formation in general, and understanding nature of dark matter. So we are all agree that we should study dwarf galaxies, right? But also, as you can guess, since they are small and faint, it's hard to find them. So let's talk about how we can find them. This is a traditional way, right? Using resolved stars. The idea is basically you image a sky, create a catalog, right? You make a spatial. Okay, let's see. You make a spatial plot. Did it happen? Yep. Nothing happens, right? You don't see an overdensity. But if you select stars in color magnitude space that are consistent with old and metal poor stars and just plot those here, then you see an overdensity, right? Voila, you discover an ultra-faint dwarf galaxy. This technique has been very efficient in finding ultra-faint dwarf galaxies around Milky Way, around M31, and faint dwarf galaxies out to 4 megaparsecs. So we did a little bit test to see what is possible in the next decade with Rubin. So we created MAG observations of dwarf galaxies, different size, shape, luminosity, and injected those images, those MAG observations into our deep imaging that is comparable to that 10-year depth of LSST. And here are our results. You can see we have the size luminosity plot, and the blue color means it is high detectability, yellow means low detectability, and this is at 1.5 megaparsec, so edge of the local group. And at the edge of the local group, our census will be complete down to absolute magnitude of -5. So I'm not saying we are going to find them. We are going to be complete for these very faint systems out to edge of the local group. So this is very exciting, and this is how these systems will look like, the faintest ones will look like in 10-year LSST. And then we did other distances, 3.5 megaparsec. This is how they will look like, and we will be complete down to absolute magnitude -7, which is the brightest ultra-faint dwarf galaxies. And then at 5 megaparsec, we will be complete down to absolute magnitude of -8, which is the faintest classical dwarf galaxies. So beyond 5 megaparsec, it is hard to resolve stars, so the results are diminishing, but that's not the end of the world. We can still use integrated light searches, right? The basic idea is remove the bright sources and then apply different smoothing scales to reveal diffuse light. And this technique has been used very efficiently to find faint dwarf galaxies up to 12 megaparsecs, but it is less sensitive to the faint ones. You can basically find the much brighter dwarf galaxies with these techniques. So they're incredible and very complementary, right? But unfortunately, both techniques failed to find this little guy. This is Tucana B. And as you can see, it is not completely resolved. It has only a few bright resolved stars and some smudgy light. So both techniques fail to find this guy. And when we find this, we get the deep imaging, resolve individual stars, and it is one of the faintest things that we find in isolation. It is an ultra-faint dwarf galaxy. In isolation, the nearest galaxy to this guy is 500 kiloparsec away. So it might be a definitive example of an ultra-faint dwarf galaxy that has been quenched by ionization because it has no young stellar population. And confirming a key driver of galaxy formation and evolution at lowest mass scales. So that's exciting, and it's also signaling us a new era of discovering ultra-faint dwarf galaxies at the extreme edge of Milky Way. So that's great, but we only find this guy because Day-Sand was bored during a telecon, and he happened to open up Legacy Viewer and just happened to find it. And we don't expect Dave to look at all the Rubin data, to look all of the images, to find these interesting things, right? So we started a new survey that is called Seamless. So the idea is to connect the regimes between well-resolved and unresolved regime, target the semi-resolved regime. So it's not just in between. And as you can see, our logo even transitions from resolved to unresolved. So this is our awesome team, highlighting Jeff, Gwen, Sasha, and Claire, who are on the workshop here. Please say hi to them. And the idea is basically using integrated light searches, standard applied to the legacy survey, it will just give you million candidates. And then use a CNN algorithm, you train objects, train with known resolved and semi-resolved dwarfs that will give us 1,000 candidates, and look at visually look those and pick the highest confident systems, and that is sensitive to both, as you can see, blue and red systems. So here are showcase of our seamless discoveries. As you can see it with range of luminosities, colors, and shapes. And we get the HSD observations of these things and resolve them individual stars. And we find quite diversity between them. And one thing that I will highlight is, I promise, we are actually probing a very diverse environments here. I am just giving an example. This is the 3D environments of some of the candidates. So the purple is for Milky Way mass galaxies, green is the LMC mass galaxies, and orange is SMC mass galaxies in the environment of our dwarfs. As you can see, we are probing from complete isolation to satellites and some group environments, probably backsplash galaxies. So we are reaching our goal. We are really probing all environments. We are not relying on these satellite galaxies for the first time. And we place those new discoveries into context with known dwarfs. And this is size luminosity plot. Colored ones are discoveries. And I will highlight a couple of discoveries that we made. And starting from the faint one, so San-C is very next to Leo T. If you don't know what Leo T is the faintest known gas-bearing dwarf galaxy around near Milky Way and nearly quench. So it is one of its kind. So we got super excited to see that we are probing a size luminosity very next to it. And our San-C is very isolated. It is between Sen-A and M83 group, but it is midway, so it's far away from both of them, quite isolated. And when we look at the color magnitude diagram, I highlight only the comparable regions here, right? Leo T has some blue young stars, but Sen C doesn't have anything, although it is much more isolated. Interesting. So another example is Hydrus A, and it is sitting next to Leo P. Again, it's very interesting because Leo P is the only known faintest star-forming galaxy in isolation. So it's again very hard to find these guys. So we got excited that we find this. It is quite isolated, just like Leo P. And when we look at the color magnitude diagram, again, Leo P has these blue stars, while Hydrus A doesn't have. So even in isolation, in similar size and luminosity, these systems show very diverse evolutionary paths. So that's very interesting. And these are the other systems that we find. Again, they are one of the most faint isolated systems that's known. You might notice that I have been emphasizing isolated constantly, because most of our understanding of dwarf galaxies relies on satellite dwarfs. And isolation is important because it's free from the impact of major galaxies, right? So they are the cleanest examples. So we are quite excited, and I'm going to highlight again the field before seamless. This is the field, isolated dwarfs, distance to stellar mass. The bright ones are discovered with the H1 surveys. They are star forming. And the other ones, Leo P was also actually discovered with H1. Jahak, Tucana B, and Sculpture A, all discovered with visual inspection. Again, just handful. And now with Seamless, we are filling this gap, and we will continue filling this gap with Rubin, applying our algorithm to the Rubin data. And look, I'm just advertising that more candidates will be observed with Hubble and Roman. We just got approved to observe these things. And I will advertise that in addition to applying AI algorithms to find faint galaxies, we are also starting citizen science project with Rubin, DP2. So it's coming very soon. So stay in tune. It's called Rubin Blobs and Blurs. So join us to find the faintest galaxies with the DP2. And with that, my takeaway notes: dwarf galaxies are cool. We need to find them. And Rubin will help us to find faint and more distant ones. And please join us in our citizen science project.
Great. Thank you so much, Burchin. Our next speaker is John Franklin Crenshaw. Oh, do you have
I'll just go ahead and say my name is John Franklin Crenshaw. I am a Rubin postdoctoral fellow here at Kavli Institute for Particle Astrophysics and Cosmology. I'm mainly down at Stanford, but I'm up here at SLAC fairly often as well. And today I'll talk a lot about the cosmology I'm interested in doing with Rubin, but I'll say I'm also involved in the active optics system. Yeah. It disappeared. All right, we appear to be back. Yes, I'm John Frank Crenshaw, and I'm going to talk about the thing I'm most excited to do with Rubin, which is to use the Rubin Observatory to use LSST to map cosmic structure in the high redshift universe from redshift about 3 to 5. And to give you a brief preview, these black curves down here, these are the redshift distributions we kind of expect for the regular 3x2 point weak lensing analyses we're planning to do with the Rubin Observatory. But what I really want to do is use these colorful distributions down here, these high redshift galaxies, to kind of push LSST's lens further into the universe and kind of learn about the high redshift universe as well. And so I want to spend the next 10 minutes kind of motivating you why this is an interesting thing to do. So as was alluded to earlier by Sean, we have this beautiful cosmological model, lambda CDM, that's really under strain from all the precise data sets we've thrown at it. We've known for about a decade now about the Hubble tension, the H-naught tension, probably more than a decade. The last few years, we've seen these new emerging tensions from DESI, from the Dark Energy Survey, and other supernova compilations, suggesting that maybe there's also disagreement in omega matter, the amount of matter in the universe, the sum of the neutrino masses, dynamical dark energy. This dynamical dark energy thing, we've always thought that it was probably a cosmological constant that's driving the acceleration of the universe, right? But recent evidence is suggesting that maybe it's not a constant, maybe it's evolving in time. That's what this curve on the right over here is showing. The x-axis is the redshift, and the y-axis is the relative energy density of dark energy. And you can see that these constraints published by DESI are not flat, but rather they prefer this evolution. And in particular, in the high redshift universe, above redshift 0.5, the energy density is actually growing in time. And this is a very weird phenomenon called phantom dark energy that, if this is true, it's even more surprising than we would have expected. Similarly, there are these results from DESI and DS that perhaps neutrino mass is too low. So we know from neutrino oscillation experiments that neutrinos have to have mass, even though we don't know the absolute mass scale. And those oscillation experiments also provide a minimum mass, a floor to what the sum of the masses has to be. And so this plot on the right, these are also constraints from DESI. And this vertical line here that I marked with the red arrow up there, that's the minimum mass that neutrinos have to have in order to agree with neutrino oscillation experiments on the ground. You can see these colorful contours, these posteriors from DESI, really want neutrino mass to be below that limit. There's very little left kind of above that limit. And so this is kind of emerging as a possible tension. And even weirdly, it kind of looks like they prefer negative neutrino mass, which again shouldn't be interpreted at face value as negative neutrino mass, but it's kind of a sign that there's something that we're missing in this cosmological model. And of course, all of these kind of tensions, these constraints come from data in two very different regimes. One is the very high redshift regime, so around redshift 1100. This is where our CMB experiments like Planck and WMAP provide really nice precision constraints on lambda CDM. And then the rest kind of comes from what I'll call the low redshift regime. So kind of reaching up to about redshift 2 these days. These are large scale structure surveys like DES and DESI, and our supernova surveys as well. We have to connect the constraints, to get our best constraints, we want to connect these two data sets. And that requires kind of extrapolating the evolution of the universe, kind of this in-between region that we have not yet constrained. And doing so requires assuming a cosmological model like lambda CDM. And more so today, kind of assuming that model to connect these two regimes, things just aren't quite working. So we want to kind of push into this high redshift regime and kind of fill in this kind of unconstrained epoch of the universe. But there's other reasons we care about these high redshifts as well. So for one, this is a huge volume that's kind of being left on the table that we haven't used to drive our cosmological models yet. So for a fixed area of the sky, there's actually way more volume at high redshifts than at low redshifts. This is just the familiar geometric fact. There's more space far away from you than there is really close to you. And this curve on the right here, this blue curve is kind of showing you how much volume is there per unit redshift at different redshifts. And so you can see it grows to high redshifts. It kind of weirdly turns over. That's that familiar turnover in the angular diameter distance, kind of a weird thing about the expansion of the universe. But in general, there's actually about 3 times more volume between redshifts 2 to 5 than there is in all of the redshift less than 2 universe. Another great thing is that structure is more linear at high redshifts. Stuff is less evolved, less baryonically modified. And so we know how to extract cosmological information out of that. And so that's what this curve in gold here is showing. Kind of the scales to which that we can kind of extract cosmology from the data grows exponentially with redshift. And so in some sense in cosmology, there's like exponential more information at high redshifts than at low redshifts. And then finally, 2 of these really big mysteries, in fact, the 2 that I highlighted, right? The really low neutrino mass and the phantom dark energy. There's great evidence now that these preferences are driven by a specific feature in the data, which is that the geometric information from BAO and the CMB and the CMB power spectrum, they disagree about how much distance there is between the surface of last scattering and the domination of dark energy. And so the length of this distance scale, this tension, is what drives these really peculiar features. And so pushing to higher redshifts, getting a better understanding of what is the expansion rate happening, what is it doing in this era, will provide very nice kind of illumination on these kind of weird mysteries that are emerging. So luckily, LSST is going to detect more than 100 million galaxies above redshift of 2. These galaxies will trace this high redshift large scale structure. We can use their clustering to kind of map out these webs in the dark matter. They'll lens the CMB behind them. And these are kind of the redshift distributions we expect. So we have these 3 different redshift distributions. These come from dropout galaxies. And so what are dropout galaxies? These are high redshift star forming galaxies. We often call them Lyman break galaxies because that break is what causes this dropout. So this green curve here, this is a curve of a star forming galaxy. And you can see that it's bright and it's rising as you go towards the UV. That's the sign that it has these bright O and B stars. It's forming new stars. But there's this really sharp feature where the flux disappears. And that's because all of the flux at shorter wavelengths than this is bright enough, is energetic enough, I should say, to ionize neutral hydrogen. So any neutral hydrogen in the host galaxy and its CGM and the IGM along the line of sight, all that neutral hydrogen gobbles up these photons, and those photons disappear from our line of sight. And so if you look at the galaxy in the top, these are postage stamps. These are from JWST. You can see the galaxy is quite visible at long wavelengths. And as you go to shorter wavelengths, it disappears. And we say it drops out of the image. And so by looking for galaxies that are invisible at short wavelengths, but quite visible at long wavelengths, this allows us to find these high redshift galaxies. I should say, this is a nice example I picked from JWST. This is way above the redshifts that we will see. But LSST can find these at redshifts 3, 4, and 5 by looking for galaxies that disappear in the U band, disappear in the G band, disappear in the R band. So here is an example from DP1. I haven't had enough time yet to do this with DP2, but this is a dropout galaxy that's at redshift 3.7. So you can see it is quite visible in RIZ, but when you look at the G band, it's barely there. You can barely see it, but it's mostly disappearing, right? And so when we select for these galaxies that disappear in the G band in DP1, you can see we get a nice spike in the redshift distribution around redshift 3 to 4. And we have a little bit of contamination from the low redshifts. That's something we'll have to deal with. And here are some forecasts for what we expect when we get the full LSST data set. Actually, this is just for year 1 forecasts. So on the left here, we have constraints on omega matter. So this is the amount of matter in the universe. And S8, this is kind of how clumpy, how much structure there is in the universe. The dashed black line, these are the constraints that you expect from the regular kind of quote unquote low redshift weak lensing analyses. That orange contour is what we expect from this high redshift large scale structure with these Lyman break galaxies. And so you can see that these galaxies by themselves are not as constraining as the low redshift weak lensing analysis, but they have very different degeneracy directions in this space. And so the combination of the two gives you a lot more leverage than you might have otherwise expected just from the increase of the data volume. What's really nice here is you can see this degeneracy direction really helps constrain omega m. And this omega m is really tied to that metric about how, like, what's that distance interval in the high redshift universe. On the right over here is basically the exact same plot, but here is W naught WA. These are parameters that constrain the evolution of dark energy. And so you can see that even though dark energy is weaker in high redshift universe, this still provides us leverage to measure dark energy because now you have a long redshift baseline. You can really see how things evolve over long time periods in the universe. So LSST will be the discovery engine. It's going to find all these high redshift galaxies for us. But in order to do this well, to extract all the information we need from our data, we're working really hard to combine data from a number of different telescopes to perform this analysis. So the Roman Space Telescope, launching very soon, will provide really great information that helps us understand that low redshift contaminant population that I talked about. DESI is trying to do this spectroscopically. They're going to target a subset of the redshift 3 galaxies. So that'll provide nice correlations and cross calibration for our redshift distributions. We're trying to collect a bunch of medium band data, both on DECAM, the IBIS survey, and the Subaru Telescope's NIJI survey. Again, those are for understanding our contamination rates, our redshift distributions. And then these CMB experiments, ACT and Simons, we need to calibrate the galaxy bias of our populations. So we'll add CMB lensing cross correlations to our sample. I lead the LBG topical team in the desk, and so we have a really active, nice new team working on a lot of stuff. And I'm very happy that we're really building a strong LBG team here at SLAC and at Stanford. And I want to shout out particularly these two students who are both in the room, Ben Sherwin and Leo Sykov. I want to shout them out because they both have posters at this meeting talking about our work on Lyman red galaxies. So Ben's done really excellent work showing how sensitive we are to photometric redshift errors. And Leo's doing really excellent work trying to simulate kind of the joint combination of all these data sets that we need to do this analysis. So go check out their posters and ask them questions. So in summary, the cosmological model is starting to crack under the scrutiny from all the data we're bringing to it. But LSST can provide a huge amount of new data in the high redshift universe that'll let us test this model in new ways than we've ever done before. And so we're really hoping that 5 years from now, we're going to have, maybe we'll resolve some of these questions. We'll have a whole new set of questions to answer. And it'll be a really exciting time to do cosmology. Thanks.
Thanks so much. We have one final speaker, Carrie Holt. She's online. So Carrie, you can go ahead and unmute and share your screen.
Great, thank you. All right, can you see me? Okay. Thank you so much for having me. Thank you to the organizing committee for inviting me and also for letting me do this talk virtually when I ended up not being able to make it in person. So today I'm going to talk to you about what drives cometary activity in the outer solar system. And by outer solar system, I mean the region beyond the asteroid belt, beyond Jupiter. Oh, and I forgot to say, I love that I'm Carrie Holt. I'm a LSS TGA Catalyst Fellow, and I'm at Las Cumbres Observatory. So why do we care about comets, distant comet activity? I'm sure you're all wondering. And that is because comets are remnants of planet formation. So in the early solar system, you had the rocky and icy planetesimals that coalesced together to make the planets. And the leftover planetesimals are what are now our asteroids and comets. And we can, because they experienced less processing than these larger planets, we can probe them to get a better understanding of the conditions of the early solar system and the protoplanetary disk. And this is especially true for long period comets. Long period comets are comets with orbits of thousands to millions of years that are perturbed inward from the Oort cloud. The Oort cloud is this giant spherical icy reservoir, 20,000 to 100,000 AU from the sun. And when these comets are perturbed inward from the Oort cloud by galactic tides or passing stars, before they were perturbed, they've been in this cold storage for most of their lifetime. And so when they come in towards the sun, we're able to observe what we believe to be some of the most pristine materials that we can observe directly because they were in cold storage for so long. And so essentially, if we understand the sort of composition and thermal history of these bodies, we can then have a better understanding of the different formation regions and how our solar system has evolved. So when we're observing activity, near sun activity, and by near sun, I mean within 3 to 5 AU from the sun, not super, super close to the sun, activity is dominated by water ice sublimation. Water ice is the most dominant volatile in comets that we know of, and it really drives the activity near the sun. This is also where most of our observations occur. One, because the comet's super bright because it's really active from water, but also because it's when it's closest to us. Further from the sun, water ice sublimation is inefficient. So beyond 5 AU, something else must be driving the activity. This is likely more volatile ices such as CO and CO2, which are the other two major volatile ices in comets. There's also a water amorphous to crystalline ice transition further from the sun as well that cause activity. And so these volatiles have been observed in distant comets, but they're not as well understood as this near sun activity that we have a lot of observations of. So if we observe this distant activity, we'll be able to observe the most pristine and volatile materials before they experience significant thermal processing when they approach closer to the sun. And fortunately, we're able to do that because now comets are able to routinely discover these surveys are now able to routinely discover comets outside of that water ice sublimation region. So you can see this image here with discovery distance and discovery date, the amount of comets and how far we've been able to discover them. I'll just point out a couple of things. One, you might see this vertical ledge here, and this is when many major moving object surveys began. You'll see that there's a few very distant discoveries, very few of them, but really incredible. And then you might see this maybe cutoff-ish area around 10 AU. And it's been unclear, is this where comets are like all turning on, or is this just the limits of our current survey capabilities? So if we want to observe these distantly active comets, unfortunately, when they're very distant, means they're very faint, which means they're very difficult to observe. And now I'm sure you would all agree that we should just aim JWST at every single distantly active comet, but I don't think that is in the cards just yet for a large survey. So what we can do instead is use broadband optical photometry. This is more accessible to smaller ground-based observatories. It also has more time available so that we can really monitor these comets over time and get an idea of how they brighten. And when we look at how they brighten, we can associate the trends that we see, how they brighten, with different processes that might be driving the activity. For example, we might see a surge of brightening here, which maybe correlates to a temperature where some ice is beginning to sublimate. So maybe it's entering this new sublimation regime and it contains that ice. That's the idea. So to do this near the sun has been done. It's pretty well characterized. It's been observed since the Oort cloud was first postulated in the 50s. This is the behavior and trends that we currently use to characterize comets and also to estimate future brightness. So this is the trend that we see near the sun. It is essentially a single slope with log heliocentric distance that does not vary. And so when we're estimating future brightness behavior, we will fit a single slope to the known observations and then project forward to estimate future brightness. However, this is all based on observations that occurred within 3 to 5 AU from the sun when the activity was dominated by water ice sublimation. So it stands to reason that maybe outside where water ice sublimation is inefficient, that this trend may be different. And that is exactly what we found. So with the LCO Outbursting Object Key Project, or LOOK project, we were able to monitor over 50 comets over 6 years, observing them approximately every 3 days using the LCO 1 meter network. And this has allowed us to get really uniform, frequently cadenced observations, very similar to what we expect to get from LSST. All of the comets in our sample were discovered between 5 and 9 AU from the sun, and so far our entire sample has shown similar brightening behavior, and this is what you see on the right. So you see they brighten more rapidly further from the sun, and then it sort of shallows off. And we've been able to create a new model that better characterizes this brightening behavior than the traditional model, as you can see in this image. Now, I will say this is not necessarily true of all comets. For example, C2017K2, which was discovered beyond 15 AU and found to be active up to 24 AU, might very well have a different brightening behavior, but these particular group that's discovered in this regime all look the same. And these results have implications for the Comet Interceptor mission. And if you don't know what the Comet Interceptor mission, I will tell you because it's one of my favorite things to talk about. So the Comet Interceptor mission will launch from the Earth in 2029 and essentially sit in a parking orbit at L2 and wait for a yet to be determined long period comet to enter into the inner solar system. Once you choose the target, the spacecraft will then travel to meet the target and intercept it, release 2 probes, and carry out science for the very first time on a long period comet in situ, which is very exciting. So our results, the implications for the Comet Interceptor mission, first of all, this is really going to help us make better predictions for the activity levels that the spacecraft will experience at encounter. Because we don't want to get to, we want to have enough activity to be really good for our instruments, but we also don't want to be so close that we destroy our probes. But we also might not have as much warning time as we originally expected. So a comet discovered with current surveys at around 9 AU from the sun, we originally thought with traditional model, we would maybe discover at around 21 AU and have about 7 years warning time between discovery and encounter. However, with this new model, it is more likely that we might only get 1 more extra year of time than we do now, and only a 3-year window from discovery to encounter. And this is important, especially when doing our target selection, because the spacecraft may take up to 3 years to intercept the target. Beyond Comet Interceptor, why in the science realm, like we're talking about, what does this mean for solar system formation and evolution? So we're seeing this rapid brightening further from the sun, and it's right around that region where we expect the onset of CO2 sublimation, as you can see in this figure on the left. It's also, again, right near sort of where the water ice transition is. But going with the, so does this mean that most comets are CO depleted? CO is more volatile but it can also drive activity even further from the sun than CO2. How could so many comets be CO depleted, especially if they're coming in from the Oort cloud for the first time and it's been less processed? So one idea is that maybe it's been thermally processed during its scattering into the Oort cloud. Maybe it came very close to the sun. Maybe there was processing occurring in the Oort cloud by galactic cosmic rays, or they were formed in a totally different region during formation. Like many other sciences, we need many more observations to get a better understanding of the population and what was really driving this activity. Fortunately, LSST will discover comets farther from the sun than ever before. This is going to give us a much larger sample size to test our models and to test these theories. LSST depth will also test the limits of these discovery distances, and we can really see, is that actually a shelf in discovery distance, or will we continue and observe much further out? Hope to observe the onset of distant activity, which can give really good insight into what is driving it. And almost certainly hope to observe the most distantly active comet with LSST, which is exciting. So I'll just end with making sure you understand that the drivers of distant cometary activity cause a brightening behavior that is different from the behavior observed near the sun, and that LSST is poised to transform our understanding of that distant comet activity. Thank you.
Thanks so much, Carrie. So I'd like to thank all of the speakers on behalf of the SOC and all of us. We're a little short on time, so if you're online, please use the Plenary Slack page to ask your questions. And if you're here in person, you can do that or come find the speakers over coffee. Thanks so much.